15,800,000,000 miles. That is how far Voyager 1 is from Earth right now, as you watch this. It has been traveling for 48 years. It moves at 38,000 miles per hour, fast enough to circle our planet in 39 minutes. And yet, in the grand architecture of the cosmos, it has barely moved at all. This is the story of the loneliest objects we ever made, where they went, what they found, and what it means that we sent them at all. There is something gentle about thinking of them now. Two small machines, built by hands that are mostly no longer with us, drifting in directions they cannot change. They do not know how far they have come. They do not know how far they have left to go. They simply continue. The number you are looking at, 15 billion miles, is so large that the word mile almost stops meaning anything. Light itself, the fastest thing in the universe, takes more than a day to travel from Voyager 1 back to the antennae waiting on Earth. When the engineers in Pasadena send it a command, they send the message and then they wait. And then they wait, and then they wait. And when the reply finally arrives, the spacecraft they are speaking to has already moved another 1.5 million miles further away. There is no rush out there. There is only forward. Settle in. Slow your breathing. This is going to take a while. We are going to follow Voyager into the dark. And in following it, we are going to find some of the loneliest things our universe has ever made. Some of them are machines we built ourselves. Some of them are worlds we did not even know existed when Voyager launched. Some of them are stars, drifting in places that have never had a name. By the end of this journey, you will know where they are going, and what they will pass on the way, and what will be left of them in the deep future after the sun has died and the stars have gone out and the universe itself has begun to grow cold. For now, all you need to do is breathe. The journey is already underway. It started long before you opened your eyes today, and it will continue long after you close them tonight. Let us begin. In the late 1960s, a young mathematician at the Jet Propulsion Laboratory in California was running orbital calculations on a problem nobody had asked him to solve. His name was Gary Flandreau. He was, at the time, a graduate student working on a summer project, 26 years old, untenured, not yet famous, doing the kind of patient mathematical work that academic outsiders sometimes do, hoping that one of their lines of inquiry will turn out to matter. This one would. What Flandreau discovered that summer would shape the next half-century of space exploration. Flandreau noticed that, in the late 1970s, the 4 outer planets of our solar system, Jupiter, Saturn, Uranus, and Neptune, would line up in a way that does not happen often. Not in a straight line, exactly. The planets do not work that way, but they would arrange themselves along a long, slow curve, each one perfectly positioned to act as a gravitational sling, throwing a spacecraft from one to the next, and the next, and the next. A single spacecraft, properly launched, could visit all 4 of them. The trick is something called a gravity assist. When a spacecraft passes close to a large planet, the planet's gravity pulls it in, swings it around, and flings it back out, faster than it arrived. The energy comes from the planet itself, which slows down by an amount so small no instrument could measure it. The spacecraft, having borrowed a little bit of speed, sails onward toward its next target. Without these gravity assists, a journey to Neptune would take more than 30 years and require enormous amounts of fuel. With them, the same journey could be completed in 12. The mathematics turn an impossible expedition into a barely possible one. The alignment Flandreau had discovered was rare. It occurs once every 175 years. The previous opportunity had passed in the 1800s, before anyone alive could have used it. The next one would not come until the year 2152. Nobody alive in the 1970s would see it twice. Nobody alive in the 1800s had seen it once. The window was opening for the first time in human technological history, and it would close again before any of the engineers who walked through it would draw their last breath. NASA approved the mission quietly. The budget was tight. The country had just been through Apollo, the Vietnam War was ending, the economy was struggling, and the public mood was not generous toward expensive science projects. The team was given the bare minimum to build 2 spacecraft, one to serve as a backup in case the other failed, and a window of about 7 years to design, construct, test, and launch them. The spacecraft had to be ready in time. If they missed the window, the planets would move on without them. The team built them in time, just barely. The launches were scheduled for the late summer of 1977, separated by only a few weeks. Voyager 2 went first, on the 20th of August. Voyager 1, despite its lower number, launched second on the 5th of September. The lower number reflects its faster trajectory. It would arrive at Jupiter first, even though it left second. The universe gave us one chance. We took it. On each of the 2 Voyagers, bolted to the side of the spacecraft, there is an object that does not strictly need to be there. It serves no engineering purpose. It collects no data. It runs no experiments. It is a 12-inch disc of gold-plated copper, encased in an aluminium jacket, and it has nothing to do with the mission. It is called the Golden Record, and it is one of the strangest things our species has ever made. The idea was simple. The 2 spacecraft were going to leave the solar system. They were going to wander through interstellar space for an unknown amount of time, possibly forever, and there was a small, non-zero chance that somebody, somewhere, eventually, might find them. The committee that designed the record was chaired by Carl Sagan, and it included scientists, artists, musicians, philosophers. They were given a question to answer. What do you say to the universe? The record contains 115 images, encoded in analog form on the disc itself. There are photographs of children, of women breastfeeding, of a man eating an ice cream cone. There are pictures of mountains, of forests, of cities. There is a photograph of a sunset over the Pacific Ocean. There is a diagram of the structure of DNA. There is a picture of a man and a woman holding hands. There is a fetus before birth, curled in the dark. There are 35 natural sounds. The sound of wind, the sound of rain, the sound of footsteps, the sound of surf breaking on a beach, the sound of thunder, the sound of fire, the sound of a kiss, the sound of a humpback whale singing in deep water, a sound so beautiful that the committee debated for weeks whether to include it, and finally decided that no message to the universe would be complete without it. There are greetings spoken in 55 languages. Many of them are now endangered. Some of them are now dead. There is a greeting in Akkadian, a language that has not been spoken in 2,000 years. There is a greeting in Hittite, a language that fell silent more than 3,000 years ago. There are greetings in languages that have only a few hundred living speakers today, and that may not survive the century. Voyager carries them onward regardless. The languages on the record will outlive the languages on Earth, even if the species that speaks them survives. There are 90 minutes of music: Bach, Beethoven, Chuck Berry, a Georgian folk song called Chakrulo, sung by a male choir, a Navajo night chant, a Peruvian wedding song, a Japanese shakuhachi piece called Suru no Sugimori, which translates roughly as cranes in their nest, Mozart, a piece by the Bulgarian shepherdess Valia Balkanska, Indian classical raga, a Senegalese percussion piece, The choices were meant to represent the breadth of human musical expression across cultures, across centuries, across continents. The instructions for how to play the record are engraved on its cover in the universal language of mathematics. A diagram shows the proper rotation speed expressed in units of the natural frequency of a hydrogen atom. The committee assumed that any civilization capable of finding the record would also be capable of reading those instructions. If a civilization can build the kind of technology required to detect a small object drifting between the stars, they can probably figure out how to play a record. The selection process took months. Carl Sagan was haunted by it. He wrote later that every choice they made felt impossible. What do you leave out? What do you put in? Should the record reflect what humanity is, or what humanity wishes to be? They argued. They cut things. They added things. They cut them again. There were disagreements about whether to include images of war, of suffering, of poverty. Some members of the committee felt the record should be honest about human darkness. Others felt that the record was a message, not a confession, and that there was no point in introducing ourselves to the universe by listing our failures. In the end, the darker images were left out. The record presents Earth at something closer to its best. It is perhaps a small lie. It is also perhaps the kind of lie that a species tells about itself when it wants to be remembered well. The record contains a recording of a mother speaking gently to her newborn child. It contains the sound of a human heartbeat. It contains the sound of laughter, recorded from a single, unnamed, laughing person. It contains the brainwaves of Anne Druyan, who would later marry Carl Sagan, recorded while she was thinking about what it felt like to fall in love. Her thoughts, in some encoded form, are now sailing through interstellar space. Every language on that record is now either endangered or dead. Every civilization that contributed something is either gone or unrecognizable from the form it took in 1977. The record has outlasted everything it tried to represent. And it has not even left the solar. It is the 14th of February, 1990. Voyager 1 has been traveling for 12.5 years. It has visited Jupiter and Saturn. It has photographed their moons, their rings, their storms. It is now 3.7 billion miles from Earth, on the far side of the solar system, moving outward, away from everything it has ever seen. Its cameras are still working. They will not work for much longer. NASA needs the power they consume for other instruments, more important instruments, ones that will keep functioning long after the cameras have gone dark. The decision has been made to shut them down. Before they shut them down, Carl Sagan has an idea. He has been arguing for years that the spacecraft should turn around just once and take a photograph of Earth from where it is. From 3.7 billion miles away, there is no scientific reason to do this. The image will not be useful. Earth, from that distance, will be smaller than a single pixel. It will be barely visible. It will look like nothing. NASA resists. The operation requires precise pointing of the cameras, careful planning, the use of resources that could be spent on real science. Sagan persists. He writes letters. He makes phone calls. He explains, again and again, that the image will not be scientifically useful, but that it might be humanly necessary. Eventually, NASA agrees. The cameras turn around. Voyager 1 looks back across the entire solar system, past Saturn, past Jupiter, past Mars, until it sees, in a long beam of scattered sunlight, a single pixel of pale blue. Earth. Home. Everything anyone has ever known. The image is striking less for what it shows than for what it does not show. There are no continents visible, No oceans, no countries, no mountains, no cities. There is only a tiny, faint speck of blue, smaller than a mote of dust caught in a sunbeam, hanging in a vast field of empty black. The beam of light around it is sunlight, scattered through the camera's optics. The dot itself is 12% of 1 pixel, the smallest thing the camera could record. Just barely visible, barely there at all. Carl Sagan looked at the image and wrote something. He wrote a great many things about it over the years, but the most well-known passage goes something like this. "That dot," he said, "is here. That is home. That is us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever lived out their lives. Every saint and sinner, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, every hopeful child, every inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on a mote of dust suspended in a sunbeam. Our posturings," he wrote, "our imagined self-importance, the delusion that we have some privileged position in the universe are challenged by this point of pale light. Our planet is a lonely speck in the great enveloping cosmic dark. In our obscurity, in all this vastness, there is no hint that help will come from elsewhere to save us from ourselves." He thought that the image, when people looked at it, might help them, might soften the edges of all the things humans do to each other. It is hard, he believed, to look at that pale blue dot and continue to take seriously the small differences that divide us. The river of blood spilled by emperors trying to expand their reach across a tiny portion of a tiny dot. The faiths killing each other over interpretations of the same handful of texts. The arguments over who gets which piece of the pixel. To Sagan, the image was a call to humility. It was a call to take care of the dot, because the dot was, for the moment at least, the only home we had. There was nowhere else to go. There was no escape route. The universe, as far as we could see, did not have anything else for us. Every story we had ever told ourselves, every history we had ever written, every dream we had ever dreamed had happened on that single fragile speck of blue. The photograph was taken on the 14th of February, 1990. After it was taken, Voyager's cameras were powered down. They have not been turned back on since. They never will be. The power has long since been redirected to instruments that are still doing scientific work. That was the last time it looked back. The two Voyagers had separated by then into different directions. Voyager 1 had taken a steeper path, pushed upward and out of the plane of the planets after its encounter with Saturn. The reason was a moon called Titan, Saturn's largest moon, shrouded in a thick atmosphere, hiding what lies beneath. NASA wanted a close look. The flyby required Voyager 1 to alter its trajectory in a way that would bend its path out of the ecliptic, the flat plane in which the planets orbit, and send it on a steeper, more vertical course out of the solar system. It worked. Voyager 1 got its close look at Titan. The photographs revealed nothing of the surface. The atmosphere was too thick. The cameras saw only the top of a thick, orange-brown haze. It would take another spacecraft, decades later, to actually see Titan's surface. But Voyager 1 had done its job. It had measured the atmosphere's composition, its temperature, its structure, and it had paid the price. After Titan, it was bound for nowhere in particular, just steeply upward and outward, away from everything. Voyager 2 had stayed lower, continuing on to Uranus and then Neptune, the only spacecraft, before or since, to visit all 4 of the outer planets. At Uranus, in 1986, it discovered 10 new moons and 2 new rings. At Neptune, in 1989, it discovered 6 more moons, and the great dark storm that had been raging in the planet's atmosphere for what we now believe to be centuries. After Neptune, Voyager 2 also turned outward, and the 2 spacecraft began their long drift into separate parts of the sky. Voyager 1 is heading in the direction of the constellation Ophiuchus, the Serpent Bearer. It will not arrive at any star in Ophiuchus, but it is heading in that general direction. The constellations, of course, are not real objects. They are patterns we draw between stars that happen to fall in similar parts of our sky. The stars in Ophiuchus are not actually near each other. They are at various distances from Earth, scattered across thousands of light years of space. Voyager 1 will pass between them, eventually, on its way to somewhere else. Voyager 2 is heading toward Telescopium, a small, faint constellation in the southern sky, named after the instrument that revealed so much of what we now know. Telescopium is not visible from most of the northern hemisphere. It is one of the lesser-known constellations, defined in the 18th century by the French astronomer Nicolas Louis de Lacaille, who named many of the southern constellations after scientific instruments. There is also Microscopium, the microscope. There is also Octans, the octant. The southern sky, in its naming, reflects an age when science was new, and astronomers wanted to honor the tools that had made their work possible. Neither spacecraft is flying. That is a word for things with engines, things that can choose where to go. The Voyagers have no engines, in any meaningful sense. Their tiny thrusters can adjust their orientation, can keep their antennae pointed at Earth, but they cannot change their speed or direction in any way that matters. They are not flying. They are falling, perpetually, in a straight line, through a universe that does not care that they are there. Once the gravity assists ended, once the planets had finished throwing them outward, the spacecraft became objects of pure momentum. Physics does the rest. Newton's first law, written down 3 centuries ago, governs them entirely. An object in motion stays in motion unless something stops it. Nothing is going to stop them. The thrust that launched them is long gone. The fuel that powered the maneuvers is mostly used up. What remains is a small amount of hydrazine, just enough to keep the antennae pointed home for a few more years. After that, the spacecraft will tumble. They will lose contact with Earth. They will continue. There is no destination. There is no rescue mission. There is no way to stop. There is only forward into a dark that is older than anything either of them will ever encounter. But Voyager was not the first. Others went out before it, and some of them are already lost. The 3rd of March, 1972, a bright Florida morning, an Atlas Centaur rocket on Launchpad 36 at Cape Canaveral. The flame ignites, the rocket lifts, and the first object humanity has ever designed to leave the inner solar system begins to climb. Pioneer 10 was small, by modern standards, less than 600 pounds. Its main dish was 9 feet across. Its scientific instruments were the smallest and lightest the team could build. It carried no cameras worth speaking of, no high-resolution imaging systems, none of the equipment that would later make Voyager famous. The team that designed it knew the spacecraft would be the first of its kind. They built it conservatively. They built it to survive, not to impress. It was a scout. Nobody had ever sent a spacecraft past Mars before. Nobody knew what was out there. Pioneer 10's first task was to find out whether a spacecraft could even survive the journey. The first obstacle was the asteroid belt. At the time, Scientists were not sure what the asteroid belt actually was. Some believed it was a dense field of rocky debris, the remnants of a destroyed planet, packed so closely together that a spacecraft trying to pass through it would almost certainly be hit by something. The popular conception of the asteroid belt, in science fiction and in the public imagination, was something like a shipwreck graveyard full of tumbling rocks that would tear a passing vehicle to pieces. Others thought it was sparser, more navigable. They argued that the asteroids, while numerous, were spread across such an enormous volume of space that the probability of a collision was small. There was no way to know without going there. Pioneer 10 entered the belt in the summer of 1972. The team at NASA waited. The spacecraft transmitted its telemetry hour by hour, day by day, and the engineers watched for any sign of damage, any sign that it had struck something, any sign that the journey was about to end. It did not. The belt turned out to be much emptier than expected. The asteroids, even though there are many of them, are spread across an enormous volume of space, so vast that the average distance between them is greater than the distance from Earth to the Moon. Pioneer 10 sailed through unharmed. It detected a few small impacts from dust grains, but nothing larger than that. The science fiction version of the asteroid belt turned out to be wrong. The belt is mostly empty. The asteroids are real, but they are scattered. In December of 1973, Pioneer 10 reached Jupiter. What it found there was a world unlike anything humanity had imagined. The radiation belts around Jupiter, generated by the planet's powerful magnetic field, were 10,000 times more intense than Earth's Van Allen belts. The spacecraft was hardened against radiation, but the engineers were not certain it was hardened enough. As Pioneer 10 made its closest approach, the radiation levels began to affect its instruments. Some data was lost. Some images came back garbled. Some onboard systems briefly malfunctioned, then recovered. But the spacecraft survived. It pulled away from Jupiter, accelerated by the planet's enormous gravity, and continued onward, the first machine humanity had ever sent past the last of the inner planets, into territory we had never even photographed up close. It also did something more subtle. By measuring Jupiter's gravitational pull during the flyby, Pioneer 10 confirmed the precise mass of the planet. By passing through Jupiter's magnetic field, it mapped the field's structure for the first time. By photographing the planet from close range, it returned the first detailed images humanity had ever seen of a gas giant. The cloud bands, the great red spot, the complex structure of the atmosphere, all of it was unknown before Pioneer 10. All of it was changed by what it sent home. Nobody knew what was out there, Pioneer 10 told us. And then it kept going. Bolted to the antenna struts of both Pioneer 10 and Pioneer 11, there is a small plaque. It is made of gold anodized aluminium. It measures 6 inches by 9 inches. And like the golden record that would come later, it has nothing to do with the mission. The plaque was designed by Carl Sagan and Frank Drake, with illustrations by Linda Salzman Sagan. Its purpose, like the records, was to communicate something to anyone who might one day find the spacecraft. The design is simple, in the way that designs intended to be read by minds we cannot imagine must be simple. In the upper left of the plaque, there is a diagram of a hydrogen atom. Hydrogen is the most common element in the universe. Its physics are the same everywhere. The diagram shows the atom transitioning from one quantum state to another, releasing a photon with a specific frequency. This frequency is the unit of measurement for everything else on the plaque. Distance is measured in multiples of the wavelength. Time is measured in multiples of the frequency. This means that any civilization that finds the plaque anywhere in the universe should be able to read it. They will know about hydrogen. They will know about its quantum states. From there, they can derive every other number on the plaque. Below the hydrogen diagram, there is a figure of a man and a woman. The woman stands to the left. The man stands to the right, with his right hand raised, in a gesture meant to be interpreted as either a greeting or a sign of peaceful intent. Neither figure is clothed. Behind them, drawn to scale, is a silhouette of the Pioneer spacecraft itself, so that any finder will know how large the humans depicted are compared to the object that carried them. In the center of the plaque is the most ambitious element. It is a map, a pulsar map, specifically. 14 lines radiate outward from a central point, which represents the Sun. Each line points toward one of 14 pulsars, which are rapidly rotating neutron stars that emit beams of radiation at extremely precise intervals. The length of each line indicates the distance to its pulsar. The pulse period of each pulsar is encoded in binary along its line. If a civilization knows about pulsars and knows their periods, they can use the map to locate our star in the galaxy. They can find where we live. The map is, in effect, a return address. It is the only return address our species has ever sent into deep space. The plaques sparked a small controversy on Earth when they were unveiled. Some objected to the nude figures. They felt the figures were obscene, or that they sent the wrong message about humanity. The committee responded that the plaques were intended to be honest about the biological form of the species sending them, and that hiding the body would have been a strange choice. Some argued that the man and woman were not sufficiently representative of human diversity. The figures were drawn as composites, intended to represent humanity as a whole, but the resulting illustration looked, to many critics, like a specific subset of humanity rather than a universal one. Others argued that pulsars would be useless navigation markers by the time anyone found the plaque, because pulsars slow down over time and their periods would have changed. Carl Sagan responded to these criticisms in his usual way. He listened, he acknowledged the points, and then he said simply that every choice they had made was imperfect, but that silence seemed worse. The plaques are still out there, both of them. One on Pioneer 10, somewhere in the constellation Taurus, one on Pioneer 11, somewhere in the constellation Aquila. They are unread. They are unfound. They are quiet. In a way that suggests, perhaps, that they will remain quiet for a long time, perhaps forever. Pioneer 10 spent the next 2 decades drifting outward. It crossed the orbit of Saturn, then Uranus, then Neptune. In 1983, it became the first human-made object to pass beyond the orbit of all the major planets. Each year, the signal it sent back to Earth grew weaker. This is not a malfunction. This is simply physics. The radio signal Pioneer 10 transmitted was generated by a power source that was steadily decaying, the heat from a plutonium-238 thermoelectric generator that was producing less and less electricity every year. And the signal itself, even at full strength, had to spread across an ever larger volume of space as it traveled, becoming more diffuse with every mile. By the late 1990s, the signal was almost imperceptible. The 70-meter Deep Space Network dish in Goldstone, California, was being used to listen for it. The dish is one of the most sensitive radio receivers ever built. It can detect signals weaker than the energy released by a snowflake landing on a city block. The signal Pioneer 10 was sending by then was less than 100 billion billionths of a watt. So faint that even the giant dish at Goldstone had to listen for hours to be sure of what it was hearing. On the 22nd of January, 2003, the dish at Goldstone detected one final, faint whisper from Pioneer 10. It was less than half a watt of power, transmitted across more than 7.5 billion miles of space, arriving at Earth as a signal so weak that only the largest antenna in the world could distinguish it from background noise. The signal had taken 11 hours to make the journey. By the time the team confirmed they had received it, the spacecraft had moved another several 100,000 miles further away. After that, nothing. It was not a malfunction. It was not a disaster. It was simply the physics of distance and entropy. The signal had become too faint to hear. NASA stopped listening, not because they had given up, but because there was nothing left to detect. The spacecraft was still functioning, presumably. It was still emitting a signal, presumably. But the signal had crossed below the threshold where any antenna on Earth could pull it out of the cosmic background. It was lost to noise. Pioneer 11 had gone quiet earlier. In September of 1995, its antenna had drifted away from Earth due to the slow rotation of the spacecraft over decades. The contact was simply lost. There was no way to recover it. The spacecraft is now heading in the direction of the constellation Aquila, the Eagle. In approximately 4 million years, it will pass close to one of Aquila's stars. By then, there will probably be no one to know. Nobody on Earth knows exactly where Pioneer 10 is anymore. We know its initial trajectory. We know how fast it was moving when we last heard from it. From these, we can calculate roughly where it should be, given the gravitational effects of the Sun and the planets and the major bodies in the outer solar system. But the further it goes, the larger the uncertainty becomes. After enough time, we cannot say with any precision where it is. It is out there. It is moving. It is carrying its plaque. The spacecraft itself is, presumably, still intact. There is very little in deep space to damage it. Cosmic rays will gradually degrade some of its components. Micrometeoroid impacts will, over millions of years, slowly erode its outer surfaces. But the bulk of the spacecraft, the central body, the plaque bolted to its struts, will survive far longer than any human civilization. It is on a journey that will outlast everything that built it. It is the loneliest object we have ever lost. For decades after Pioneer 10 and Pioneer 11 had finished their primary missions, something strange began to appear in their data. It started in the early 1980s. The team that was tracking the spacecraft using the Deep Space Network noticed that their trajectories were not quite what the equations predicted. The Pioneers were decelerating slightly, by an amount so small that it took years of careful measurement to even detect it, but it was real. The deceleration was constant. It was directed toward the Sun. It was not large, only about 8 times 10 to the negative 10 meters per second squared, which is so small that it would take a year to slow a spacecraft by less than 1 mile per hour. But it was there, and nobody could explain it. The mystery is called the Pioneer Anomaly, and it generated serious scientific debate for 30 years. Many explanations were proposed. Some scientists suggested it was caused by dark matter, an unseen mass in the outer solar system that was pulling the spacecraft back. The idea was that perhaps the asteroid belt, or some uncatalogued population of icy bodies in the outer solar system, had enough gravitational pull to produce the effect. Careful searches did not find any such bodies. The dark matter hypothesis, when applied to the Pioneers, did not match the data. Some suggested it was caused by a new kind of physics, a deviation from general relativity that only became visible at very long distances. The idea was that gravity might not behave exactly the way Einstein's theory predicted, especially at the edges of solar systems, where accelerations are very small. If this were true, it would mean a revision of our most fundamental theory of how the universe works. The implications were enormous. Some thought it might be evidence for modified Newtonian dynamics. often called MOND, a theory that proposes gravity behaves differently in regions of very low acceleration. MOND had been developed to explain the rotation curves of galaxies, which behave as if there is more mass in galaxies than we can see. Some MOND advocates pointed to the Pioneer anomaly as further evidence that gravity has properties we have not yet fully mapped. Some thought it might be an error in measurement or a flaw in the calculations. They argued that the anomaly was an artifact of how the trajectories were being computed, not a real physical effect. They pointed to small errors in the models of the sun's pressure, the effects of solar radiation on the spacecraft, the precise mass of the outer planets. Maybe the equations were not wrong, but the inputs were. Hundreds of papers were written. Conferences were held. The anomaly became one of the most discussed, unsolved problems in space physics. If it was caused by new physics, the implications were enormous. It would mean that our understanding of gravity, the most basic force in the universe, was incomplete. It would mean that the textbooks would have to be rewritten. In 2012, after 30 years of debate, a team of researchers finally solved it. The answer was thermal radiation. The spacecraft, like all spacecraft, generate heat. The plutonium power sources produce heat as a side effect of generating electricity. The instruments inside the spacecraft produce heat as they operate. The radio transmitter produces heat. The onboard computers produce heat. Heat has to go somewhere, and on a spacecraft in deep space, it can only radiate away into the vacuum. It turns out that the heat from Pioneer 10 and Pioneer 11 was not radiating away evenly in all directions. It was radiating more strongly off the back of the spacecraft than off the front. Photons of infrared radiation, leaving the spacecraft in one preferred direction, were producing a tiny but real thrust in the opposite direction. The spacecraft were, very slowly, being pushed backward by their own body heat. The thrust was small, but it was exactly the right magnitude to explain the anomaly. The researchers used detailed thermal models of the Pioneer spacecraft, accounting for every component, every panel, every instrument. The model predicted exactly the deceleration that had been observed. After 30 years, the mystery was solved. There was no new physics, there was no dark matter pulling on the Pioneers, there was no modified gravity, there was just heat, doing what heat always does, leaving the spacecraft as infrared light and exerting a tiny pressure as it went. The result was, in its own way, beautiful. We had built machines so precise that their own body heat showed up in their trajectories. And for 30 years, we thought it might be new physics. The Pioneers were so well built, and our tracking of them was so precise that the engineering had outrun the modeling. We were measuring effects we had not thought to predict. There is something quietly impressive about that. The Pioneers, by the time the anomaly was solved, had been operating in deep space for 40 years. They were not designed to last that long. Their original mission was only meant to be a few years. And yet, here we were, 4 decades later, still receiving data so precise that we could detect the gravitational equivalent of a snowflake's worth of pressure on a moving spacecraft. The Pioneers were the first. Voyager went further, but neither of them was the fastest. That distinction belongs to a piano, the 19th of January, 2006. An Atlas V rocket on Launch Pad 41 at Cape Canaveral. The launch had been delayed twice already, by weather and by wind. On the third attempt, conditions were finally clear. The rocket lifted off, the upper stage burning to its absolute limit, throwing the spacecraft outward with more energy per kilogram than any rocket had ever delivered before. The spacecraft accelerated to 36,373 miles per hour. It was the fastest object that humanity had ever launched. For comparison, the Apollo astronauts, on their way to the Moon, took 3 days to cover the distance from Earth to lunar orbit. New Horizons crossed the same distance in 9 hours. The spacecraft's destination was Pluto. At the time it was designed, Pluto was still considered the 9th planet of our solar system. It would be reclassified as a dwarf planet a few months after New Horizons launched, when the International Astronomical Union changed its definition of what a planet is. The reclassification was based on the discovery that Pluto was not alone out there. Other objects, similar in size and composition, had been found in the same region of the solar system. Pluto was no longer special. It was one of many small worlds in a vast outer ring. But the mission did not care. It continued onward, regardless. The team that built New Horizons did not consider Pluto's demotion a problem. To them, it was always going to be a remarkable destination, regardless of what category it belonged to. The reclassification was a matter of definitions. The world itself was still there. The journey was still worth taking. New Horizons would take more than 9 years to reach Pluto, even at its enormous launch speed. The distance was simply too great. By the time of its arrival, the team that designed the spacecraft had been working on the mission for more than 15 years. Many of them had started their careers on the project. Some had retired before it arrived. One of the original principal investigators died during the journey. He did not live to see what his spacecraft would find. The spacecraft itself is roughly the size of a grand piano. It runs on approximately 200 watts of power, which is less than 2 household light bulbs. It carries 7 scientific instruments, each one chosen for the minimum possible weight and the maximum possible scientific return. Every gram on the spacecraft had to be justified. Every component had to earn its place. It is, in many ways, the descendant of the pioneers and the Voyagers, designed by people who had spent their entire careers learning from those earlier missions. It carries no cameras as ambitious as Voyager's. It carries no golden record. It does carry, on board, a small portion of the ashes of Clyde Tombaugh, the astronomer who discovered Pluto in 1930. His ashes are sealed inside the spacecraft, riding along on the way to the world he found. When New Horizons reaches Pluto in 2015, Tombaugh's ashes will be the first human remains ever to leave the solar system. Clyde Tombaugh was a farmer's son from Illinois. He was 24 years old when he discovered Pluto, working as an assistant astronomer at the Lowell Observatory in Arizona. He spent a year comparing photographic plates, looking for a faint dot that moved against the background of stars. When he finally found one, he had discovered a planet, or what we then called a planet. He spent the rest of his life as one of the most respected planetary astronomers of his generation. He died in 1997, 9 years before the launch of the spacecraft that would carry him home. He never saw it, but he is on it, and it took him there. The 14th of July, 2015, after 9 years of travel, New Horizons reaches Pluto. The closest approach is 7,760 miles above the surface. The spacecraft is moving so fast, just under 9 miles per second, that the entire flyby lasts only a few hours. There is no time to slow down. There is no time to enter orbit. New Horizons has fuel only for small course corrections. It will sweep past, take as many photographs as it can, and continue outward into the cold beyond. The team at Johns Hopkins University Applied Physics Laboratory, where the mission is operated, has prepared for this moment for more than a decade. Every instrument has been programmed in advance. Every photograph, has been scheduled. Every measurement has been planned. The spacecraft will execute the flyby autonomously on its own, because the signal delay between Earth and Pluto is 4.5 hours each way. 9 hours for a round-trip message. Real-time control is impossible. The team can only watch. The night before the closest approach, there is a moment of fear. The spacecraft, just hours from its destination, goes silent. Communication is lost. For a few hours, no one at Mission Control knows what has happened. They have spent 15 years preparing for this. They have spent 9 years traveling toward it. And now, with the encounter only hours away, the spacecraft has gone dark. It is a software glitch. Engineers diagnose it remotely. The spacecraft has gone into a safe mode, a protective state it enters when it detects a problem it cannot resolve. The team reboots its computer, restores the science programs, and points it back at Pluto. They have less than a day to fix everything. They fix it. The flyby proceeds as planned. What they see, when the data finally arrives, is a world that nobody expected. There is a heart. A great, bright nitrogen ice plain in the shape of a heart, stretching across an area roughly the size of Texas. The team names it Tumbo Regio, after the man whose ashes are riding along on the spacecraft. The heart is one of the most recognizable features in the history of planetary science. It becomes, almost immediately, the iconic image of Pluto, the face of a world that until that moment, no one had ever seen up close. There are mountains of water ice rising 11,000 feet from the plains, hard as rock at the temperatures of the outer solar system. There are nitrogen glaciers, flowing slowly across the surface, glittering in the faint sunlight, which is about 1,000 times dimmer at Pluto than it is on Earth. There are dunes, which should not exist on a world with so thin an atmosphere, but which do exist, made of solid methane particles, moved by winds that should be too weak to move anything. There is haze. A thin, blue atmospheric haze layered in multiple bands above the surface, stretching 90 miles up into the sky. The haze is made of complex hydrocarbons, organic molecules formed when sunlight interacts with the nitrogen in Pluto's atmosphere. The molecules drift downward, slowly, eventually depositing on the surface, where they give Pluto its characteristic rust-colored tint. There may be a subsurface ocean. The evidence is indirect, but compelling. Pluto's heart-shaped plain sits at an unexpected position on the planet, in a place that suggests the dwarf planet may have rotated over geological time in response to the mass of the ice in the heart itself. This kind of slow rotation, called true polar wander, is most easily explained if there is a layer of liquid water beneath the surface, allowing the heavier ice above to redistribute itself. If the ocean exists, it is kept liquid by the slow heat of radioactive decay deep in Pluto's core. The world we expected to be a dead, frozen rock turns out to be active, dynamic, and possibly even hospitable in a very limited sense to whatever strange biochemistry might survive in absolute dark, at temperatures hovering just above absolute zero, beneath a shell of nitrogen ice. There are 5 moons. Charon, the largest, is half the size of Pluto itself and orbits so close that the two worlds are mutually tidally locked. They face each other forever. If you stood on the surface of Pluto, looking toward Charon, you would see the moon hanging in the same place in the sky, never moving, never setting, a great grey companion bound to its smaller partner. The other moons, Hydra, Nix, Kerberos, and Styx, are smaller and more chaotic, tumbling in their orbits, named after creatures and places from Greek mythology associated with the underworld. We expected a dead rock. We found a world. The team at Johns Hopkins watches the images come back, line by line, frame by frame, with the 4.5-hour delay built into every observation. It is autonomous. We had designed it to go somewhere we could not reach, and then we had trusted it to do so. There were no second chances. Every photograph the spacecraft did not take would not be taken. Every measurement it did not make would not be made. The flyby was a single, unrepeatable event, and the team had to trust that they had programmed it correctly. They had. It worked. We received more information about Pluto in those few hours than we had collected in all the 85 years since its discovery. New Horizons did not stop at Pluto. It could not stop. It had no fuel for braking, no engine large enough to enter orbit. It sailed past Pluto, took its photographs, and continued onward into the Kuiper Belt, the broad ring of icy objects that surrounds our solar system beyond Neptune. The team at Johns Hopkins had an idea. There was enough fuel for one more close approach. They began searching, using the Hubble Space Telescope, for a small, icy body that the spacecraft could reach within its remaining lifespan. They found one. It was given the temporary designation 2014 MU69. It was later named Arakoth, which means sky in the Powhatan Algonquian language. It is located 4.1 billion miles from the Sun. To put that in perspective, the Earth is roughly 93 million miles from the Sun. Arakoth is 44 times farther away than that. The Sun, from Arakoth, is no longer a disk. It is just the brightest star in the sky, and only just brighter than the others. On the 1st of January, 2019, just after midnight, New Horizons flew past Arakoth. It is the most distant object ever visited by a spacecraft. What the spacecraft saw, when its images were transmitted back to Earth, was strange and beautiful. Arakoth is what astronomers call a contact binary. It is two objects, two separate small icy bodies that formed independently in the early solar system and then gently merged billions of years ago when their orbits brought them together at low speeds. They are now permanently fused, like two snowballs pressed together, with one large lobe and one smaller lobe. The larger lobe is called Arakoth itself. The smaller one is called Wenum. Together, they look like a flat, reddish snowman, frozen for the past 4.5 billion years in the form they took when they first touched. Arakoth's surface is smooth. There are very few craters because there are very few large objects in the Kuiper Belt to strike it. It is reddish because of the same hydrocarbon haze that coats Pluto, slowly depositing over geological time. It has barely changed since the formation of the solar system. It is older than anything on Earth. It is older than the Earth itself. The Earth, when it formed, was hot. Its surface was molten. Most of the original material that made it has been recycled through plate tectonics, through erosion, through volcanism, through the slow geological processes that have remade the planet's surface over and over again in the 4.5 billion years since. The oldest rocks ever found on Earth are about 4.4 billion years old, and they are tiny crystals of zircon, preserved in younger rocks that themselves have been reworked many times. Almost nothing on Earth's surface today is more than a few 100 million years old. Arakoth has not been recycled. It has not been melted. It has not been disturbed. It is almost literally a piece of the original solar system preserved. Its surface is what it was when the first plants started to grow on Earth, when the first fish swam in the first oceans, when the first dinosaurs walked, when the first humans appeared. It has been sitting out there, in the dark, While everything we know about Earth has happened, all of it, every era, every age, every story, New Horizons photographed it. It measured its temperature, its composition, its structure. The temperature on Arakoth is roughly 40 degrees above absolute zero, which is to say about -390 degrees Fahrenheit. At that temperature, nothing happens. Chemistry stops. Even most physics slows down. Arakoth is essentially in a deep freeze that has been preserving it since the solar system began. And then New Horizons kept going. It is still going. It has now crossed the heliopause, the boundary where the sun's influence ends, and it has entered interstellar space, the second human-made object to do so after Voyager 1. It is now the loneliest object we have ever launched that is still functioning. Its instruments are still operating. Its radio is still transmitting. The team at Johns Hopkins is still receiving data. The spacecraft is still small, still piano-sized, still running on 2 light bulbs of power, and it is still moving outward, alone, into the silence beyond Pluto. The 25th of August, 2012. The team at the Jet Propulsion Laboratory in Pasadena, California, has been watching their data carefully for months. Voyager 1, by then, is more than 11 billion miles from Earth. Its signal takes 17 hours each way. The spacecraft is approaching something nobody has ever crossed before. It is approaching the heliopause. The heliopause is the edge of the sun's influence. It is the boundary where the solar wind, the stream of charged particles flowing outward from the sun, becomes weak enough that it can no longer push back against the pressure of the interstellar medium, the thin gas and dust between the stars. Beyond the heliopause, the sun's influence ends. The space outside is no longer the sun's space. It belongs to the galaxy. Scientists had been debating where, exactly, the heliopause was for decades. Different models gave different predictions. Some put it at 100 astronomical units from the sun, where 1 astronomical unit is the average distance from Earth to the sun. Others put it at 200. There was no way to know without going there. Voyager 1 had been heading toward it for 35 years. On the 25th of August, 2012, the spacecraft crossed it. The team detected the crossing by watching 3 different instruments simultaneously. The cosmic ray detector showed a sudden increase in cosmic ray density as the spacecraft moved out of the sheltered region where the solar wind blocks most galactic cosmic rays. The solar wind sensor showed a sharp drop in particle flux as the wind that had filled the inner solar system fell away to almost nothing. And the magnetometer showed a slight change in the direction of the magnetic field. These 3 observations taken together told the team that Voyager 1 had crossed into interstellar space. It had crossed a boundary that no human-made object had ever crossed before. It had become, in that moment, the first object created by intelligent life on Earth, as far as we know, to leave the cocoon of our star and enter the rest of the galaxy. But the instrument that gave them the most beautiful piece of data was the plasma wave detector. It detected, faintly but persistently, a hum, a low, sustained oscillation at a frequency of about 8 to 9 kilohertz. The plasma in interstellar space vibrating against the spacecraft's antenna, producing a sound that the spacecraft heard and recorded and sent back to Earth. Space is not silent. It hums, quietly, constantly, for no one. For decades, science fiction had described interstellar space as silent. The vacuum, after all, cannot carry sound waves the way air does. There is nothing to vibrate. But the interstellar medium is not a perfect vacuum. It contains very thin plasma, which can vibrate electromagnetically in ways that an antenna can detect. The hum that Voyager 1 heard was the sound of that plasma oscillating at its natural frequency, the heartbeat of the empty space between the stars. If you listen to the recording, what you hear is barely audible, a faint whisper of sound, more like a soft breath than a tone. But it is constant. It does not stop. It has been there for as long as the galaxy has existed, and it will be there for as long as the galaxy continues to exist. For most of the history of the universe, no instrument has ever heard it. We built one. It heard it. It told us. In November of 2023, 11 years after the heliopause crossing, Voyager 1 began sending corrupted data. For 5 months, the signal arriving at Earth was garbled, unreadable. The cause was unknown. The team at JPL, including several engineers who had retired and been called back to help, who had worked on the mission for 40 years, began diagnosing the problem at a distance of 14 billion miles. The signal delay at that distance was 22 hours each way. A round-trip message took 44 hours. The engineers could send a diagnostic command, and then they had to wait nearly 2 days for the reply. They could send another command. They had to wait nearly 2 more days. They could send another. They had to wait nearly 2 more days. The diagnostic process, which on a nearby satellite would take minutes, was taking weeks. They worked through it. They identified the fault, eventually. It was a single chip in the spacecraft's flight data system, a memory module that had become corrupted, possibly by a cosmic ray strike, possibly just by age. They devised a workaround. They rerouted the telemetry data around the damaged chip, using parts of the spacecraft's memory that were still functioning. The fix worked. In April of 2024, Voyager 1 began transmitting readable data again. We repaired a 47-year-old machine 14 billion miles away, using a signal that took nearly a full day to arrive in each direction. There are engineers alive today who have worked on this mission their entire careers. Some of them were children when it launched. Some of them have retired and been brought back because they are among the only people on Earth who still remember how the old systems work. The mission has a strange property in that its operating manuals were written in 1977 in a programming language that almost no living engineer has used for anything else. To keep Voyager alive, NASA has had to keep some of its original engineers alive too, in a working capacity. There is no younger generation that knows this system from the ground up. There cannot be. The mission continues. Beyond the heliopause, beyond the place where the sun's wind gives way to the gas of the galaxy, Voyager continues. It is in interstellar space, technically, but it is far from done with our neighborhood. The solar system does not end at the heliopause. It continues outward, much further than most people realize. Surrounding the inner solar system, far beyond the orbit of Neptune, beyond the Kuiper Belt where Arakoth drifts, there is a vast spherical shell of icy bodies. It is called the Oort cloud, named after the Dutch astronomer Jan Oort, who first proposed its existence in 1950. The cloud is theoretical, in the sense that no one has ever directly observed its inner edge, but its existence is the simplest explanation for where long-period comets come from. The comets that swing through the inner solar system every few thousand years originate, we believe, from the Oort cloud. They are not native to the inner solar system. They are visitors from much further out. The cloud extends from approximately 2,000 astronomical units to over 200,000 astronomical units from the Sun. That outer edge is roughly halfway to the nearest star. The Oort cloud is, in effect, a tenuous halo that surrounds our entire system, marking the gravitational territory of the Sun against the rest of the galaxy. It is theorized to contain trillions of comets. Trillions. Each one is the leftover debris of the formation of the solar system, flung outward by gravitational interactions with the giant planets billions of years ago, captured into long, slow orbits that take them millions of years to complete. They drift in the dark, in the cold, in the vast volume of space that surrounds our small inner system. Most of them never come near the inner planets. Most of them never come near anything. They simply continue their slow, lonely orbits, occasionally disturbed by the gravitational pull of passing stars, but mostly undisturbed for the entire history of the solar system. Voyager 1 will not reach the inner edge of the Oort cloud for approximately 300 years. 300 more years of travel after 47 years already covered just to reach the beginning of the cloud. The journey we are watching is in some sense only just starting. It will take approximately 30,000 years to pass through the cloud entirely. 30,000 years. The entire history of human civilization from the first cities to today is about 12,000 years. Voyager will spend more than twice the entire span of human civilization just crossing the Oort cloud. Even when Voyager has finally crossed the outer edge of the Oort cloud, it will not have reached another star. Proxima Centauri, the nearest star to our own, is approximately 4.2 light-years away. At Voyager's current speed, the journey would take 73,000 years. It is not heading toward Proxima Centauri. It is heading toward the constellation Ophiuchus, which is much further away than that. There is no end to the journey. There is no place it is trying to reach. The trajectory was set when the planets finished throwing it outward decades ago, and nothing in the universe is now adjusting it. The spacecraft simply continues, and the universe through which Voyager is moving is itself moving. The galaxy is rotating, slowly, dragging the solar system along with it at about 230 kilometers per second, which is about 143 miles per second. The galaxy itself is moving, drifting toward a region of dense mass called the Great Attractor at about 600 kilometers per second or 370 miles per second. The Great Attractor is itself being pulled by something even larger, the Shapley supercluster, in a hierarchy of motion that extends across the entire observable universe. Our galaxy is also being pushed. Recent observations have identified a region of unusually low density on the opposite side of the sky from the Great Attractor. It is called the local void. It is roughly 150 million light-years across, and it is almost entirely empty. The lack of mass on that side of us means that the gravitational pull on the Milky Way is unbalanced. We are being pushed away from the emptiness, toward the density. We are running, slowly, from nothing. Voyager moves within a galaxy that is itself moving. It is drifting inside a drift, inside a drift, inside a drift. Its precise trajectory, calculated relative to Earth, is one thing. Its trajectory relative to the center of the galaxy is something else. Its trajectory relative to the center of the local group of galaxies is something else again. There is no fixed frame of reference. There is no still point against which to measure motion. Imagine, for a moment, the layers of motion. Voyager moves away from the Sun. The Sun, with all its planets, orbits the center of the Milky Way once every 230 million years. The Milky Way, in turn, orbits the center of the local group, a small cluster of about 80 galaxies, bound together by gravity. The local group is part of the Virgo supercluster, which contains thousands of galaxies. The Virgo supercluster is being pulled toward the Great Attractor, while being pushed away from the local void. And the entire structure of the observable universe is, in some sense, expanding, the space between superclusters slowly growing, the distances between distant galaxies increasing with every passing year. Voyager is in all of these motions simultaneously. It is moving away from the Sun. It is orbiting with the Sun around the galaxy. It is orbiting with the galaxy around the local group. It is being pulled with the local group toward the great attractor. It is being carried by the expansion of the universe itself. All of these motions, all of these speeds, all of these directions are happening at once. The simple line Voyager appears to be drawing through space in our maps is actually a complex curve woven through layers of cosmic motion that no one ever sees, because we are all moving with them. Nothing in this universe is truly still. The universe has a habit of throwing things away. During the formation of a planetary system, when a young star is surrounded by a disk of gas and dust that gradually condenses into planets, the process is chaotic. The planets that form are large and small, near and far, and they do not always settle into stable orbits immediately. They tug on each other. They pull at each other. The bigger planets, particularly the gas giants, can disturb the orbits of the smaller ones, sending them on wild paths through the system. Most of these wild paths end in collision, or in absorption, or in stable new orbits. But not all of them. Sometimes, a planet is flung outward, away from its star, given enough energy by the gravitational chaos to escape the system entirely. It becomes a rogue planet, a world without a sun. For decades, astronomers suspected that rogue planets must exist. The mathematics of planetary formation suggested that some ejection events should occur, but it was difficult to observe rogue planets directly. They produce no light of their own, and they are not illuminated by any nearby star. The first confirmed rogue planet was discovered in 2011. It was found indirectly through a technique called microlensing. When a rogue planet passes between Earth and a distant star, its gravity bends the light from the star, briefly magnifying it. The pattern of magnification reveals the presence of the planet, even though the planet itself remains invisible. The discovery was a kind of detective work. The planet itself was never seen, only its effect on the light from a much more distant object. Since then, more have been found, and the surveys have suggested something startling. The number of rogue planets in the Milky Way may be greater than the number of stars. The estimates vary. Some studies suggest 50 billion. Others suggest 100 billion. Some recent work has proposed that the number may exceed 1 trillion. Trillions of worlds drifting through the spaces between stars, with no sun to orbit, no light to warm them, no place to call home. To put this in perspective, the Milky Way contains roughly 100 billion stars. If there are 1 trillion rogue planets, that is 10 rogue planets for every star. Most of the worlds in our galaxy may be drifting freely, without any star at all. Most of these worlds are likely small. Some are gas giants, ejected during the early chaos of their systems, still warm from their formation. Their internal heat, generated by gravitational compression and radioactive decay, may keep them above the temperature of interstellar space for billions of years. Some may have weather systems in perpetual darkness, driven by the heat of their cores rather than the light of any star. Storms in absolute night, winds blowing across landscapes that have never known day. Some may be rocky, like Earth. These would be much colder, their surfaces locked in temperatures close to absolute zero, their atmospheres frozen to the ground. They would be lifeless in any conventional sense. They would be drifting, silent, undisturbed, for billions of years at a time, until the rare chance encounter with a passing star or another rogue world. But some, possibly, may have something else. Some may have subsurface oceans, heated not by a sun, but by the radioactive decay of heavy elements deep in their cores. Beneath a thick crust of ice, miles thick, there could be liquid water. warm enough to support chemistry, possibly warm enough to support biology, if any ever formed there. If life exists on a rogue planet, it has never seen a star. It has never experienced day. It has never known what it is to look up at a sky and see anything but blackness. It exists in permanent, total, ancient dark, sustained by the heat of its own world's dying heart. The concept of a sun would mean nothing to such a life. The concept of light, of warmth from above, of the cycle of day and night, would have no place in its experience. It would know only the slow, even glow of geothermal heat, the chemical energy of the ocean around it, the patient, ancient stability of a world that is entirely its own. If such life exists, it is, in some sense, the most isolated form of life in the universe. It cannot see the stars. It does not know the universe is full of other worlds. It does not know that its world is moving. It does not know that there is a galaxy. As far as it can know, the universe consists of its ocean and the ice above it and the rock below. That is everything. We will probably never know if such life exists. Rogue planets are extraordinarily difficult to study. The nearest one, if there is one nearby, would be hidden in the deep dark between the stars, undetectable by any direct means. We can only see them when they pass in front of distant lights, briefly bending the photons that reach us. We have catalogued only a few dozen. The rest, the billions of them, the trillion of them, are invisible. Some are out there, almost certainly, drifting, quiet, carrying their oceans through the dark. The rogue planets are exiles, so are some stars. In 1988, an astronomer named Jack Hills proposed something strange. He suggested that stars could be ejected from the center of the galaxy at speeds high enough to escape the entire Milky Way. The mechanism he proposed was elegant. At the center of our galaxy, there is a supermassive black hole called Sagittarius A star. It is 4 million times the mass of our Sun. Around it, in a tight, chaotic region, there are many stars orbiting at high speeds. Sometimes, a pair of stars, a binary system, drifts too close to the black hole. When this happens, the black hole's gravity tears the pair apart. It captures one of the stars, pulling it into a close orbit, and it flings the other one outward at extreme speed as compensation. The ejected star moves so fast that it escapes the galaxy entirely. These are called hypervelocity stars. The first one was confirmed in 2005, 20 years after Hills proposed them. It was a star called SDSS J090745, 0 plus 0 24507, given the much more memorable nickname, the Outcast Star. It was moving at over 1 million miles per hour, fast enough to escape the Milky Way's gravity entirely. It had been ejected from the galactic center tens of millions of years before. By now, it was halfway to the edge of the galaxy. Since then, dozens more have been found. The first one was not unique. The galaxy is regularly ejecting stars. The supermassive black hole at our center has been throwing them outward one by one for billions of years. They move at speeds of 500 to 1,000 kilometers per second, relative to the galaxy, which is about 310 to 620 miles per second. The galaxy's escape velocity at the position of the Sun is about 550 kilometers per second, or 340 miles per second. Anything faster than that will leave forever. The hypervelocity stars are on one-way trajectories out of the Milky Way. They will never return. Their journey is, in some sense, the most extreme form of the Voyager mission. The Voyagers were sent outward by the deliberate action of humans with rockets and gravity assists. The hypervelocity stars are being thrown outward by the cold mathematics of black hole dynamics. There is no intention. There is no design. There is only the relentless gravitational logic of mass and energy. And here is the strange thing. Some of them carry their own solar systems with them. The ejection happens fast, but it is not instantaneous. A star that is flung out by a close encounter with the central black hole does not necessarily lose its planets. If the planets are far enough away from the parent star, they remain in orbit during the encounter, and they are dragged outward along with the star, accelerating with it, joining it on its journey out of the galaxy. Imagine a solar system in flight. A star and its worlds launched from the galactic center, accelerating toward the intergalactic void at 1,000,000 miles per hour. The night sky on any planet in that system would be changing, slowly, steadily. Over thousands of years, then millions of years, the stars in their sky would be thinning. The Milky Way, once a band of light across the sky, would slowly shrink. It would become a smear, then a glow, then a point, then nothing. For any beings that might exist on such a planet, watching their galaxy recede over geological time, the universe would look like it was emptying. Every star they could see would be inside their own galaxy, and that galaxy would be vanishing behind them. Eventually, the only objects visible in their sky would be the other galaxies of the local group, dim and distant. Then those would fade too, as their own runaway star pulled them further into intergalactic space. The night sky would become almost entirely dark. Eventually, if any life on such a world were patient enough to watch, the only thing visible in the sky would be their own star. Everything else would have receded into invisibility. They would be alone with their sun, drifting through a void so empty that there was for them nothing else in the universe at all. There are stars out there, right now, in flight. We know of dozens of them. There are likely many more we have not yet identified. Each one is on a journey it will never complete in any meaningful sense, heading outward, alone, toward a destination that does not exist. They will eventually slow, very slightly, due to the gravity of the galaxy pulling on them from behind. But they will not slow enough to stop. They will continue into the intergalactic dark until the universe itself runs out of time. Some of them are traveling fast enough to leave even the local group of galaxies. They are on their way out, not just from the Milky Way, but from the entire neighborhood of nearby galaxies. They will eventually be alone in true intergalactic space, with no galaxy nearby at all. The nearest other star to them will be millions of light years away. There may be planets with them, there may not. There is no way to tell from this distance. But the possibility is there. Worlds in flight, solar systems that escaped the gravitational nursery that made them and are now drifting alone through emptiness with their stars as their only company. There are stars that never made it. There are stars that were never bound to a galaxy in the first place, or that were torn loose from their galaxy long ago during one of the great gravitational events that shaped the universe. Astronomers call them intergalactic stars or orphan stars. They drift in the spaces between galaxies, belonging to nothing, illuminating nothing, orbiting nothing. The mechanisms by which they come to exist are various. Some are the result of galactic collisions. When two galaxies merge, a process that takes hundreds of millions of years, many of their stars are flung outward, away from the merged system, by the chaotic gravitational interactions of the merger. Others are the result of tidal stripping, when a smaller galaxy passes too close to a larger one, and the larger galaxy's gravity strips away the outer stars of the smaller one. Still others may have been ejected from globular clusters, dense balls of stars that orbit galaxies, sometimes losing members to the void. Perhaps 2% of all stars in the observable universe exist in this way. It does not sound like much, but the universe contains roughly 200 billion trillion stars. 2% of that is 4 sextillion stars. 4,000 million stars drifting between galaxies with no home. The number is so large it stops meaning anything. There are more orphan stars in the universe than there are grains of sand on every beach on Earth. Multiplied by every grain of sand in every desert on Earth, multiplied by itself. They are separated from the nearest galaxy by millions of light years of nearly absolute emptiness. The distances are difficult to grasp. Inside a galaxy, the average distance between stars is a few light years. In intergalactic space, the average distance from one star to another can be hundreds of thousands of light years or more. A planet orbiting an orphan star, if any such planet exists, would have a night sky unlike any inside a galaxy. There would be no stars visible to it. There would be no Milky Way. There would only be the dim smeared light of distant galaxies, millions of light years away, each one containing billions of stars too far away to resolve individually. The sky on such a world would be almost completely black. A few faint patches of light, identifiable only with telescopes, would be the only evidence that the rest of the universe exists. From any planet on such a world, the entire history of intelligent life, if it occurred, would happen in a sky that was, for all practical purposes, empty. Imagine the consequences of that. For any species that might evolve in such a place, there would be no astronomy in the way we understand it. There would be no constellations to name. There would be no mythology of the stars. There would be no celestial navigation. There would be no astrology. There would be no Galileo, no Kepler, no Newton, no Hubble, because the questions those astronomers asked could not be asked on a world where the sky was empty. The notion that the universe is large, that there are other worlds, that there is anything beyond the local environment would have to be discovered through some entirely different path. Or it might never be discovered at all. The orphan stars are not in any galaxy. They belong to nothing. Many of them have always been alone. Some of them may have been alone for the entire history of the universe, drifting through emptiness, illuminating nothing, watched by nothing. And there is something even more empty than this. The vast majority of the universe, perhaps 96% of its volume, is the void itself. Not intergalactic space exactly. Not the space between galaxies in a cluster. Something larger. The cosmic web, the great structure of the universe at its largest scales, is made of filaments and walls of galaxies, connected by sheets of dark matter. Between the strands of the web, there are voids, empty regions, hundreds of millions of light years across, containing almost nothing. These voids are not perfectly empty. There are a few isolated galaxies in them, drifting alone, with no neighbors for millions of light years. There are a few stars. There is gas, thin and diffuse. But by the standards of the rest of the universe, they are empty. Almost nothing exists in them. They are the negative space of the cosmos, the spaces between everything that is. The largest void we have mapped is called the Boötes void. It is 330 million light years across. There are only 60 known galaxies in the entire region. By comparison, a similar volume of normal space would contain about 10,000 galaxies. The Boötes void is missing more than 99% of the galaxies it should contain. It is, in cosmological terms, a hole, a place where the structure of the universe simply did not form, or fell apart, or was always empty from the beginning. Inside the Boetes void, the night sky on any planet, if any planet exists there, would be perhaps the loneliest sky in the universe. The nearest galaxy would be tens of millions of light years away. From the surface of such a world, telescopes would have to be enormous and very patient to detect anything at all. Most of the time, looking up, the sky would be empty, black, featureless, with only the dim, ancient cosmic microwave background glowing faintly in every direction, the relic of the Big Bang itself, the last echo of an event that happened 13.8 billion years ago. There may be people somewhere, on some planet, whose entire concept of the universe is shaped by living inside a void. They may not know that galaxies cluster, that filaments connect, that there are dense regions and empty regions, that the universe has structure. They may believe, instead, that the universe is mostly empty, with rare, isolated galaxies drifting alone. They would be wrong about the universe at large, but they would be right about their corner of it. Voyager is traveling through the outer edge of one of the filaments of the cosmic web. Beyond the filament, far beyond it, lies a scale of emptiness that makes the entire Milky Way look like a single grain of dust. The Milky Way is 100,000 light-years across. The Boetes void is 3,300 times larger than that, and it is mostly empty. We built our entire civilization on one mote of dust, on one strand of the web, in one galaxy, in one local group, in one supercluster, in one observable universe that may itself be one of uncountable others. And we built a small machine and sent it out into the dark to see what was there. The small machine is still going. It will be going for a very long time. In 40,000 years, Voyager 1 will pass within 1.6 light-years of a red dwarf called Gliese 445. The star is small, dim, unremarkable in any conventional sense. It is one of hundreds of billions of red dwarfs in the Milky Way. Most red dwarfs go unnamed, unstudied, anonymous. They are the most common kind of star, by far, the most numerous, the most ordinary. This one, Gliese 445, will have a visitor. Sometime in the distant future, in a year that has no name, in a future no one alive today will see, Voyager 1 will pass through its outer reaches. It will not be a close approach by any planetary standard. 1.6 light-years is more than 100,000 astronomical units. The spacecraft will pass through the outer halo of the red dwarf's hypothetical Oort cloud, if it has one, and continue on. There will be no encounter. There will be no flyby. The star will simply be the nearest thing Voyager passes for the next several 100,000 years. A ship passing in the dark, without either party knowing. If there is a civilization on a planet orbiting Gliese 445, they will almost certainly not detect Voyager. The spacecraft will be too small, too cold, too dim. Its instruments will have long since stopped working. Its radio will have long since gone silent. It will simply be one more piece of debris drifting past, and there is no reason for anyone to be looking for it. They will not be expecting it. They will not be searching for it. It will be moving past their star at 38,000 miles per hour, an enormous speed by human standards, but a small speed in galactic terms. It will take many years to pass through their region of space. It will appear, gradually, as a faint object growing brighter, and then it will fade gradually as it moves on. If they have telescopes powerful enough to see it, they might wonder what it is. A piece of debris from somewhere else. An interstellar object like Oumuamua, the strange visitor that passed through our own solar system in 2017. They will have no way of knowing where it came from. The golden record will not help them. They would have to bring it inside, study it carefully, decipher the cover, build a player. The probability of any of this happening is essentially zero. But it is not exactly zero. It is just very, very small. In 296,000 years, Voyager 1 will pass close to Sirius, the brightest star in Earth's night sky. The passage will be much further than the one near Gliese 445, but Sirius itself is so bright that the encounter, if anything could observe it, would be striking. Voyager will pass at a distance of about 4.3 light-years. The spacecraft, if it were still functioning, would see Sirius as a brilliant blue-white light, brighter than any star Earth had ever known. From Voyager's perspective, Sirius would be the brightest star in its sky for tens of thousands of years before the encounter, growing slowly larger and more brilliant, and then fading slowly as the spacecraft pulled away. There is nothing on board that will be functioning by then. The power source will have long since died. The instruments will be silent. The radio transmitter will have been cold for 250,000 years. The cameras, already powered down, will be encrusted with whatever dust has accumulated on them in the cold of interstellar space. After Sirius, there are no more close approaches plotted on the maps. The trajectory continues, but the future encounters are too far away to predict with any confidence. The galaxy itself will have rotated. Stars will have moved. Whole constellations will have rearranged themselves. The maps that astronomers draw today will be useless on those timescales. There is just open space in every direction. Voyager 2 has its own future. In about 40,000 years, it will pass close to a star called Ross 248 in the constellation Andromeda. In about 300,000 years, it will pass within 4 light-years of Sirius, on a different trajectory than its sibling. Then, like Voyager 1, it will continue into a future no one can predict. In 4 million years, Pioneer 11, silent now for decades, untracked since the late 1990s, will pass close to a star in the constellation Aquila. There will be no one to record it. The spacecraft will pass by in silence, carrying its plaque unreachable and unread. The star it passes near will continue to shine. The spacecraft will continue to drift. Neither will be aware of the other. In 8 million years, Pioneer 10, also silent, also untracked, will have moved far enough that even its rough trajectory becomes meaningless. We know it exists. We do not know where it is. Somewhere out there, moving, in a direction we can still calculate but can no longer confirm. The Voyagers will eventually share the same fate. Their trajectories are known precisely today, but not forever. Over millions of years, small uncertainties compound. Small gravitational perturbations from passing stars and dust clouds will accumulate. The exact path of each spacecraft eventually will become impossible to predict. We will know that they exist in some general region of the galaxy. We will not know exactly where they are. They will continue. We will lose track of them. The universe will continue. In 5 billion years, the sun will expand into a red giant. The hydrogen fuel that powers our star's core, the slow fusion of light atoms into slightly heavier ones, will eventually run out. When it does, the core will contract, heating itself further, and the outer layers of the sun will swell outward. Our star, which today is a yellow star roughly 900,000 miles across, will grow to a size hundreds of times larger. Its outer edge will extend past Mercury, past Venus, possibly past the orbit of Earth. If the Earth survives, which is uncertain, it will be a barren, blackened rock with no atmosphere, no oceans, no surface features that anyone alive today would recognize. The continents will have melted. The water will have boiled away, billions of years before the red giant phase, when the sun became hot enough to push our atmosphere out into space. Mars will have been heated to a temperature higher than the boiling point of water briefly, before its atmosphere too is stripped away. Every city humans have ever built, every monument, every record of our existence, every line of every book, every brush stroke of every painting, every recording of every voice, all of it gone. The Statue of Liberty, the Great Wall, the pyramids, the Library of Alexandria, long since rebuilt and rebuilt again, the Hagia Sophia, the Empire State Building, the Burj Khalifa, the Internet, every photograph anyone has ever taken, every text message anyone has ever sent, every song that was ever recorded, all of it vaporized by the slow expansion of the dying sun. Voyager 1 will still be moving. 5 billion years from now, it will have traveled, at its current speed, about 3,000 light-years from our star. It will still be inside the Milky Way. It will still be in interstellar space. It will still be carrying its golden record, the sound of rain, the sound of laughter, the sound of a mother speaking to her child. The record will have outlasted everything it was designed to represent. There will be no children on Earth. There will be no rain on Earth. There will be no Earth. But the record, carrying its evidence of all those things, will still be moving somewhere among the stars. In 7.5 billion years, the sun will collapse to a white dwarf. The expanded outer layers will dissipate into space as a planetary nebula, briefly illuminating the surrounding region of the galaxy. The planetary nebula will be one of the most beautiful objects in the sky, if anything is alive to see it. A vast, glowing shell of gas expanding outward, illuminated for a few thousand years by the central white dwarf before it fades. Then the nebula will fade, and what remains will be a small, hot, dense ember about the size of Earth, slowly cooling. The solar system will be dark and cold. There will be no light, no warmth, no source of energy. The golden record, still sealed, still intact, will still be carrying the sound of rain and surf and a mother speaking to her child. But our star, under which those sounds were recorded, will be gone. In 100 trillion years, the last stars in the universe will exhaust their fuel and go dark. The era of stars will end. The universe will enter what cosmologists call the degenerate era, a long, slow, dark period in which the only sources of energy are the cooling embers of dead stars, the slow evaporation of black holes, and the occasional collision of stellar remnants. To put this in perspective, the universe is currently about 14 billion years old. The era of stars will last another 100 trillion years. That is more than 7,000 times longer than the entire history of the universe so far. We are at the very beginning of the story. The universe is just getting started. Voyager 1 will still be moving. By then, it will be in a universe that has almost no light at all. The galaxies will still exist in some form, but they will be dim, made up of cooling white dwarfs and neutron stars rather than active, fusing suns. Anything looking out at the sky from a hypothetical planet somewhere will see only faint, red, dying lights, where once there were billions of brilliant stars. In 10 to the 22 years, that is, 10,000 billion years, Galaxies themselves will dissolve. Their constituent stars will drift apart, scattered by gravitational interactions, until the structures we know today no longer exist. The Milky Way, long since merged with Andromeda, will lose its coherence. The black holes at its center will continue to exist, slowly evaporating through a process called Hawking radiation, but they too will eventually fade. In 10 to the 40 years, protons themselves may begin to decay. This is theoretical. Some models of physics predict it, some do not. If it is true, then matter itself, the atoms that make up the golden record, the Voyager spacecraft, the pioneer plaques, the human hands that built them, will dissolve. Protons will decay into photons, positrons, electrons. The physical objects of the universe will cease to exist, not destroyed by anything in particular, just slowly fading, atom by atom, over a span of time so long that the entire history of the universe so far is, by comparison, less than a single tick of a clock. After the protons decay, there will be no atoms left. There will be no gas, no dust, no rock, no metal, no ice. There will be only thin, scattered radiation drifting through a universe that no longer contains anything we would recognize. The black holes will be the last things to remain. They will evaporate slowly through Hawking radiation over timescales that dwarf even the age of the universe at proton decay. The largest black holes, the supermassive ones at the centers of dead galaxies, will take 10 to the 100 years to evaporate completely. That number, 10 to the 100, is so large that there are no analogies for it. If every atom in the observable universe were a year, the total would not even approach 10 to the 100. It is a number that has no human meaning. It is the number that describes how long the universe must wait before its last black holes finally fade. After that, there will be nothing. The universe will be a thin, cold, almost perfectly empty space, with no structure, no light, no matter, no events. Time will continue to pass, but nothing will happen during its passing. This is what cosmologists call the heat death, the end of all change. But the information on the golden record, the pattern, the encoding, may have a strange property. If nothing disturbs it before then, the information itself, as pattern, may survive longer than the matter it is inscribed on. The sounds of Earth, encoded into the analog grooves of the disk, may exist as a pattern of disturbances in space-time even after the disk itself has dissolved. The sounds of Earth may outlast matter itself. Voyager was not a military project. It was not commercially motivated. It produced no immediate economic return. It did not benefit any politically powerful group. It did not solve any pressing crisis. It was funded, thinly, by a democratic government with a small fraction of its budget because some people in that government thought it was worth knowing what was out there. The golden record was not a diplomatic necessity. Nobody required it. It cost money to design, money to produce, money to install on the spacecraft. The team that built it had no proof that anyone would ever find it. There was no rational reason to include it. Carl Sagan and his committee chose to include it because the alternative, sending something into the dark with nothing to say, felt worse than the effort. The pioneer plaques were the same. Small, modest objects made of gold anodized aluminium designed to communicate to civilizations we have no reason to believe exist. They were included because Carl Sagan and Frank Drake decided that if there was any chance at all that someone might one day find them, the spacecraft should not be silent. We are the only species on this planet, as far as we know, that has ever looked up at the stars and felt the need to send something back, to make a gesture, to say we were here. Other animals look at the sky. They notice the moon. They migrate by the stars. But no other animal has ever, as far as we can tell, built a thing for the purpose of being seen by someone who lives among those stars. Only humans have done this. It is one of the strangest and possibly one of the most beautiful things we have ever done. The Voyager program cost approximately $865 million spread across decades. It is less than the budget of many single Hollywood films. It is less than the cost of a few large skyscrapers. It is a tiny fraction of what we spend every year on weapons, on entertainment, on the routine maintenance of civilization. It is, per unit of wonder generated, perhaps the most cost-effective thing our species has ever done. We built two small machines, smaller than a car, lighter than an elephant, made of aluminium and titanium and copper and gold and silicon. We loaded them with cameras and antennas and instruments designed to last decades. We attached to the side of each one a record of who we were, what we sounded like, what we cared about, and we sent them into the dark. We did not know if they would survive the asteroid belt. They did. We did not know if they would survive the radiation of Jupiter. They did. We did not know if they would last long enough to reach the outer planets. They did. We did not know if they would reach the heliopause in our lifetimes. They did. We do not know what they will encounter next. We do not know how long their components will last in the cold and silence of interstellar space. We do not know whether anyone ever will find them. But we sent them anyway. Knowing all of that, knowing the odds. Knowing that, more likely than not, they will simply drift forever, unread, unfound, unremarked. We sent them anyway. That is, in some sense, the most human thing about them. Not the engineering, not the science. The fact that we did it, knowing it, might not matter. The fact that we did it because someone in a meeting 50 years ago said, well, we should at least try. The fact that we attached a record to the side of a spacecraft that was already overburdened with scientific instruments, just on the chance, the very small chance, that someone, somewhere, eventually, might want to know who we were. That is who we are. Some species build nests. Some build dams. Some build webs. We build machines that we send away from us into places we will never go, carrying messages for people we will never meet. We have done it twice now, deliberately. Pioneer 10 and Pioneer 11. Voyager 1 and Voyager 2. New Horizons. 5 separate machines, all of them headed outward, all of them carrying some form of human gesture, all of them designed by people who knew that the gesture might never be received. That is what makes them lonely, in the deepest sense. Not just that they are far away, not just that they are alone, but that they were sent without any expectation of return. They were given everything they would need, and then they were let go. They are not waiting for anything. They are not heading anywhere in particular. They are simply continuing, because that is what they were built to do. And in continuing, they have become something that is hard to describe. They are not exactly ours anymore. We can no longer reach them. We can no longer help them. We can no longer change their direction. They have become something independent of us. They have become objects in the universe, not objects of human creation. They are part of the galaxy now, in the same way that any other object drifting between the stars is part of the galaxy. We made them once. We let them go. They are still going. Voyager 1 will outlast our star. It will outlast every city on Earth. Every language we have ever spoken, every book we have ever written, every name anyone has ever given to anything. It will outlast the stars themselves. Long after the last light in the universe has gone dark, long after matter itself has dissolved into a cold, diffuse fog of fundamental particles, it will, in some form, still be moving. In silence, in cold, in absolute, total dark, carrying the sound of rain, carrying the sound of a mother speaking to her child, carrying the sound of laughter. It is not lost. It knows exactly where it is. It is moving in a precisely calculated direction, at a precisely calculated speed, through a region of space whose geometry was set in motion 13.8 billion years ago by an event we still do not understand. It is the most human thing we ever made. We will never see it again. We will lose contact with it sometime in the next decade, when the last of its instruments fail and the final whisper of its signal becomes too faint for any antenna on Earth to detect. After that, it will be ours only in the sense that we know it exists. It will not communicate. It will not respond. It will simply continue. There is something quiet about that, something gentle. We did not build it to be remembered. We built it because we wanted to know what was out there, and because we had been given, for the first time in our species' history, the means to find out. We used the means. We sent 2 machines. We listened to what they told us. We learned what we could, and when they had told us everything they could tell us, when their instruments began to fail and their signals began to fade, we did not bring them home. We could not bring them home. They were never coming home. We let them go. They are not lost. They are simply far away, in the silence of interstellar space, in the deep hum of plasma vibrating against an old antenna. In the cold dark between the stars, 2 small machines continue their patient journey. They were made by a species that, 50,000 years ago, had not yet learned to write. They will, in some form, persist long after that species is gone. They are the loneliest objects we ever made. They are also the furthest reach of something we have always done, looking up at the sky and wondering and wanting to know. We were here. We sent something back. Settle in. Breathe slowly. They are still out there. They will still be out there tomorrow when you wake up. They will still be out there next year when this video is forgotten, when this channel no longer exists, when the platform that hosts it has been replaced by something newer. They will still be out there in 1,000 years. They will still be out there in 1,000,000. Space is not silent. It hums quietly, constantly, for no one.